Hi, I'm Dan the Math Guy. We're out in the field today seeing where math pops up in the real world. And what we're going to try and do today is measure the height of the tree behind me. I don't want to climb the tree with my tape measure, and I'm not very good at guessing. In fact, most people, if they just look at a tree and try and make a guess how tall it is, they're not very accurate. So we're going to do something a little more clever. I'm going to show you how very easily, with just the sun and the shadows, we can figure out how tall this tree is. All I need to do is first measure something smaller to compare it to. And I do need a little help. We have our producer Bill here with us. He's going to help me out. So what you would need is anything, like a straight stick is fine. We just want to stick something up in the ground, and we would measure how tall it is. I happen to know already this is 24 inches tall. It's a ruler I have. And all we got to do is measure the shadow. So the shadow here looks to be about exactly 8.5 inches. So what we're going to do is, I want you to think of a triangle formed by the shadow and this ruler. And this triangle here, we're going to compare that to the triangle that the tree is forming with its shadow. And the deal is they have the exact same angles. And if triangles have the same angles, then all their sides are proportional. So what that means is if we know the measurements of this little triangle here, we can adapt those to the measurements of the larger one there, which is going to get us the height of the tree. So all I need really is the length of the shadow of the tree. So I'm going to send Bill out with the tape measure to the base of the tree, and I'm going to find the end of its shadow. We'll find out how long it is. So it looks to me like the shadow ends about right here. Okay, so from the tree to the end of the shadow, I've got 22 feet, 2 inches. Turns out that's all I need. With the rest, with a little bit of simple math, I'll show you back in the studio, we'll get the height of the tree. I'll do that next. So, I didn't feel like climbing the tree with a tape measure and dropping all the way down, and we didn't really have a crane available. So this was the next best thing. But actually, this turns out to be pretty simple, and I have a little drawing on my math cam of the situation. Well, it's an artist's rendition. Do you like my tree? It looks kind of like a Dr. Seuss tree or something. But so here's what we measured. This is the ruler we had. It was 24 inches tall, and it made an 8.5 inch shadow. And then we measured the shadow of the tree, and the question was, how high is the tree from there? And what we have going for us is the ratio of the height of the ruler to its shadow should be the same for both of these objects. The sun is hitting the same angle for each one, and so all we have to do is figure out, for instance, how much higher the height of the ruler was than the shadow, and then use that same ratio to look at the tree. And so what we're really doing is forming a proportion. And mathematically, it's not too difficult to do that. Now, if you want to look at this a little geometrically, what we really have are similar triangles. So you can imagine it this way. If I had the ruler, let's say here, and I drew its shadow, if you compare that to the larger shadow, which was the tree, what you would see is two triangles that have the exact same angles in them. So these are called similar triangles, and it means all their sides are in proportion. So basically, if you find out that the shadow of the tree is 10 times larger, then the height of the tree would have to be 10 times larger. So it worked out to a simple set of ratios or proportion, and we're going to go ahead and do that for this tree here. So what I want to do is I'm going to compare the height of the ruler to the shadow length. So I'll make a little fraction for myself, 24 over 8.5. And to form a proportion, I want to look at the same ratio and the same measurements in the same order of the tree. Now, the tree has feet rather than inches, but we can get around that. We don't have to convert even, as long as we're comparing the same types of units. So here I have inches and inches, so I'm going to compare feet and feet on the larger triangle or the larger object here, which is the tree. So the height I don't know. I'm just going to use the letter H to represent the height. And the shadow is 22 feet, 2 inches. So I'm going to write that as 22 feet. Now, 2 inches, that's 2 out of 12. So I could write 22 and 2/12 inches. So what we've set up for ourselves is a little proportion, and there are several ways you could solve this, but probably the easiest one, and maybe a trick you learn in an algebra class, is cross multiplication. So the way that works is I would multiply these two diagonal numbers, and I would multiply these two diagonal numbers, and those two multiplications have to be equal. So I would have 24 times 22 and 2/12. I know that reduces to 1/6 there. And then I have that times, or equals H times 8.5. So from there, a little tiny bit of algebra. What I'm going to do is divide both sides by 8.5. And I did this ahead of time, so you didn't have to watch me punch buttons on a calculator. And H comes out to be approximately 62.6 feet. So this is actually fairly accurate if you get a good shadow of the tree. Some trees have a funny shape, but the tree we had actually made a nice tip at the top of the shadow. So we're pretty confident that this is a fairly good estimate of the height of the tree. And you can use this idea for many situations. I mean, you can even estimate something like a very large building or, I don't know, some sort of mountain or something from shadow. Well, a mountain might be a little difficult, but a building, a skyscraper would work really well. And it's a lot easier than trying to run a ruler and a ladder up the side of the thing, right? Okay, so I'm sure we're going to see similar triangles again. It's a common and useful thing, but that was one little good use for it, I think. And if you want to measure your Christmas tree or a tree in your yard, there you go. You have no excuse now. I think you might find this kind of fun. You can kind of pretend like you're on CSI or something. It has to do with forensics a little bit. So I summarized the email question. I'll show it to you on my math cam here, and then we'll talk about how you can actually figure this out. The question has to do with a detective finding a dead body, and the detective wants to know how long the body has been there, wants to know the time of death. So this is a little small. I'm going to zoom this in for you. This is just a summary, so I didn't have to write anything for you, but he finds a dead body at noon. The temperature of the body is 91.5 degrees when the detective finds it. 2 hours later, the body is 86.9 degrees, and the question is, when did the person die? So you might not know how to approach this at first, so I have to tell you a little background. How things cool, this has to do with a dead body or your coffee or anything else. What happens is the body will actually start to approach the temperature of the room, but it doesn't do it in a direct linear fashion. So in other words, the first hour, the body will actually lose more temperature than in the second hour, than in the third hour. And in fact, as the body cools toward the room temperature, it slows down at a slower and slower rate. So we need to figure out how this rate is going to go to know how long ago the body was at its normal temperature, which is 98.6 degrees. Well, if you've been watching some previous episodes, you might have seen several problems we had with exponential decay or exponential growth. That would come from something like a bank account earning money, earning interest, or a radioactive material decaying. And we talked about how that works with the equations. Well, this is actually related to the same thing. The difference here is it's actually the difference in temperatures that behaves like that. So if we take the temperature of the body and subtract it from the temperature of the room, you will get the same exponential decay. So if we're going to start working on this, let's go ahead and write down a little information. I'm going to use, tell you what, let's use B for the temperature of the body, and I'm going to use R for the temperature of the room. Okay, so this is your, let's see, we have all that information? Okay, I think we're safe here. This is your body temperature, and this is the room. That difference is exponential decay. We have a little graphic that will show you that equation. We've been using it a lot lately, so I thought maybe I should remind you how this works. If we can put the graphic on the screen, this will remind you how exponential growth and decay works. It always follows the exact same kind of pattern. So if you recognize that that's the situation you have, you can just take this formula. You notice it's based on the exponential function e, and see that the value c there is the initial value you start with, t is time, and k is a growth rate. Now k we're going to have to figure out for ourselves. That's the gist of the problem here. How are we going to figure out this value k? Well, let's think about what we know. And in fact, there's one bit of information that I haven't told you yet that was not in the problem, and our emailer did not include it, so we're going to have to make a little assumption here. And that is you need to know what the room temperature is, because that is sort of the target temperature that this body is going to approach. So I just picked a number. Let's make an assumption. Let's say it's 73 degrees. I thought it was a nice comfortable temperature for a room. So let's assume the room's been staying 73 degrees the whole time this body's been in there. All right, so if I write my formula back in here, this is for an exponential decay. It always follows the same kind of pattern. So here's my equation. This will be CE to the KT. And if you remember from our screen, what was that? Make a little room for you there. What was the C value? That was the initial starting value. So let's say we start the clock at noon when the body was found. At noon, what do we know? Well, I do know the temperature. What I really want to know is what was the starting difference in the temperatures. Well, the body was found at 91.5 degrees, and the room, I said let's make an assumption, the room was 73 degrees. So that difference is our starting value for C. And if I do my math right in my head here, that's 18.5 degrees. So that's going to be your value of C right there. That's the starting value that we have. We started the clock at noon. K, I'm going to have to find that out for myself, but we do know a couple other things. The room temperature is always going to be 73, so I'll fill that in, and then the body temperature is changing. So I'm going to take my equation, I'm going to rearrange it just a little bit. So put R on the other side. R was 73, remember, so this is stuck at 73. And I have C, I now know what that is, that's 18.5. And I have e to the kt. Your job next is to figure out what k is. And we had a little practice with this before, so what I need you to think of is take some other information you know, put it into the equation we're working on, and see if you can work backwards and figure out what k is. And we did know some additional information. If we waited 2 hours, the body was, I'm checking here, 86.9 degrees. So let's go ahead and use that information. So I'm going to keep working on my equation here. Scroll this up. This is known, so when t is 2, I'm assuming I'm measuring in hours. So when t is 2 hours, I know the body temperature was 86.9 degrees. If we plug that in, we will have everything filled in except for k. We can figure out k. That'll give us an equation. That'll describe exactly what that body temperature is doing, and then we'll try and figure out if we can answer his question when the person was killed. I was assuming he was killed. Well, someone's dead anyway. Okay, let's put these values in and see what happens. So B, 86.9 equals R, that's the room temperature, 18.5. Okay, now K I don't know, but I do know that T is 2. So here's an equation. All I have left in here is K. And if you do a little simplifying, it's going to look like some things we've done in the past. So I'm going to keep making a little room here. All right, trying not to lose our information. Let's subtract 73 from each side. I believe, let's see, what will that give me? That is 16.9, right? Yeah, I think so. 18.5 e to the 2k, all right. Divide both sides by 18.5. 18.5. I'm going to have to go on a calculator here because I don't know what this strange number is going to be in my head, but I did bring my trusty calculator. So let me see what we got here. 16.9 divided by 18.5. Okay, according to my calculator, this is about 0.9135. I don't want to round off too much. Okay, what happens after that? Well, we need to get k alone. And if you remember, this has been coming up quite a bit on our little program. I need to use logs to do this. So if you want some review for that, you can see quite a few examples in the past. But I'll remind you again how this works. If we take a natural log of each side, how would you know to do that? Well, natural log is the inverse of exponential. So if I take a natural log of each side, on the right, natural log and the e part counteract each other, and I get my exponent back to k. On the left, well, this is some strange number I'm going to get off my calculator. So here's what we have so far. 2k is natural log 0.9135. If I divide both sides by 2, we should be in business. So let's see if I can get that on the screen there. Okay. So I'm going to go on my calculator. I'm going to divide by 2, and I'm hoping that this will give us our value of k, and then we can write our equation, and it won't be too hard to answer the question. So the k I got was negative 0.045. I don't want to round off too much. I'll put 0.0452. Okay, that, I'm trying to think if that sounds right. Oh, it came out negative. Does that sound right? Well, remember, you're losing temperature, so a negative growth rate is actually correct here. I'm expecting things to decrease. So that seems to make some sense. Let's go ahead and put this back together in our equation. Okay, so I'm going to make a little room here. I'm going to put my equation all back together. So I'm copying what I had before. 73 plus 18.5 e negative 0.0452 t. If our work is correct, this should be an equation that describes the body's temperature over time. So if I plugged in a certain number of hours, this should get me any value of the temperature I like. Now, what was the original question? The question was, when did the body die? Well, what we should assume then is right when the body was killed, it was at normal body temperature. That's 98.6 degrees. And then once the body is killed, the temperature starts naturally drifting downward towards the room temperature. So I'm going to put in our value of the body, 98.6. We're going to solve and see if we can come up with how long ago that happened, the 98.6. I'm making a little assumption that he's normal body temperature, but okay, so in my value of B here, 98.6, and then the rest is going to be solving this equation and trying to figure out this value of T. So it's going to look similar now what we do here. So do a little simplifying. So I'm going to pull off 73, for instance. That should be, let's see, 25.6, 18.5, 0452, all right. And divide both sides by 18.5. So if I do that, tell you what, I'm not gonna simplify the stuff until the end here. We'll just keep writing these crazy decimals and we'll see what we come up with in the end. Okay, we're getting there. What should I do next? Well, remember what we did a minute ago to try and take care of something that's up in an exponent on an exponential function? We did natural logs. Let's do it again. So take a natural log of both sides. Okay, I'll keep writing this little fraction we got. Okay, natural log of the right-hand side. And remember how this simplifies. If you do natural log of an exponential expression, the natural log and the exponential part reverse each other, and you end up here with just what was up in the exponent. Almost done. If I divide both sides by negative 0.0452, we should be in business. So let's do that. That means my final value here is this natural log. I'll put this all in my calculator at once so we can get a good value, and I'm going to divide by the negative 0.0452. And let me see what my calculator gives me. So, kind of a messy number, I realize, but let's see what it says. 0452. I got, it says negative 7.18. You know what, that sounds a little high to me. I'm wondering if we made an error in there somewhere. I hope not, but negative 7.18. If this is correct, and I'm a little dubious at the moment, if this is correct, that means that 7 hours, a little over 7 hours ago, the body died. It was killed. If this is correct. If I made a mistake in there, I didn't see it. So if one of you see it out there, you should give us a call. Maybe, I don't know, maybe we'll have a prize for you to be the one to catch a mistake on our show. Our problem we just did on a graphing calculator, because if you look at the graph, it really shows how this body would sort of cool and approach the room temperature. And this is actually realistic. If you take your coffee and you go to Starbucks, you buy some coffee and you sit it on your counter, it will cool, but it doesn't cool in a direct linear way. So I'm going to take the equation that we came up with a minute ago, and if my equation is correct, I'm going to punch it in here. And let's see, I have 0.0452x. I think that's what we got. And what I wanted to show you, I'm going to graph this equation and also just a horizontal line at 73, and that's the room temperature. And if we do a graph of this, what you'll see is this line drifting down and then the room temperature there below it. So what you'll see is this graph slowly approaching the room temperature. Now, if I change the window a little bit, I'm going to expand this out. This is like if you waited, a little longer, if you, I don't know, left the body sitting on the floor for a while. You'll see that it starts coming down towards the room temperature. The truth is, the closer the body temperature gets to the room temperature, the longer it'll take to cool further. It starts slowing down its cooling process. So you'll see the graph is actually the steepest up near where it started at 0, and it gets less and less steep as it goes. And gradually what you'd see on the graph is would sort of parallel along that room temperature. Now, according to the math equation, it would actually never quite exactly reach the 73 degrees. In reality, of course, it probably would eventually. Well, hopefully something would be taken care of before that actually happened. All right. So that was a really interesting problem, I thought, because it really demonstrates some realistic use of math. And I know a lot of people are watching shows, cop shows like CSI, and you can kind of see people trying to figure out when bodies were killed and things like that. So I don't know, maybe get a little insight on it. And this actually came from a math class, so there you go. Now, last week, I got asked a couple tough questions. So this week, I came ready. I brought my thinking cap. So if you guys give me any really tough questions, I brought the cap to help me give me that little extra boost so I can get the problem right for you. Speaking of which, getting the problem right, I actually made a mistake last week, and I think I better come clean with it. So last week I had this really cool problem someone emailed. It was made you feel like you were like a forensics investigator or something. It was about a detective who found a dead body, and you had to figure out how long ago the body died by measuring the temperature of the body. And I remember when we did the problem at the end, I said, this answer seems a little off. Maybe I made a mistake. Well, I went home later and watched, and sure enough, I did make a mistake. So if you decide to go watch that episode and you see the dead body problem, I made just a little bonehead arithmetic error. I subtracted 2 numbers on my head and I put the wrong thing down. So if you want to go check it out, just fix my arithmetic. And the answer we got, which was roughly, I don't know, I think it was about 7 hours the body had been dead, was definitely not accurate. So if you fix my numbers, you should get an answer of around 2¼ hours. So maybe about 2 hours and 15 minutes before the detective showed up, the body was killed. All right, so I don't know, it happens sometimes, you know. We'll see how I do this time. I don't know if you noticed, but I have this pineapple sitting on my desk. So you may be wondering why I have a pineapple sitting on my desk. Well, what I was going to show you today quickly was a little bit about the Fibonacci numbers. And this is a sequence of numbers. I'll put on my math cam here. You can see what they are. And these got, I guess, a little bit more notoriety recently because the book Da Vinci Code actually mentions these as part of the, if you read the book Da Vinci Code, they set up all kinds of sort of puzzles and mysteries as part of the story. And, you know, they have, this shows up in them. And they're making a movie out of this. It's going to come out in a few months. So if you don't want to read a book, you can see it then. But these numbers showed up there. And they've actually been, had a lot of attention for many reasons. But the way it works, I'll show you what's happening here, is you take this list of numbers. You start with 1 and 1. And to get the next number, you simply add the previous 2. So 1 and 1 make 2. And then to get the next one, 1 and 2 make 3. Now 2 and 3 make 5. 3 and 5 make 8, etc. And of course, you can go forever. So sometimes they actually start this at 0. And so it depends on whether you want to start with 0 and 1 or 1 and 1. It all generates the same list of numbers after that. So I'll tell you where these actually came from the first time. It's kind of weird, but I believe he went by Leonardo of Pisa about 800 years ago, dreamed up this story that he wanted to investigate, you know, what if you had an ideal situation? You had a pair of rabbits that were going to breed and have kids. So he had a juvenile pair of rabbits, and he hypothesized it would take 2 months for them to become adults and have children of their own, and then, you know, those children could have children of their own in 2 months, and he kept this idea going, and assuming none of them died, how many rabbits would you end up with? And this is his list. This is each month how many pairs of rabbits you would end up with. And if you let these numbers go at all, you see the list gets very large quickly. I mean, I'm up to 89 here, but they get very large really fast. So I guess you probably, you know, shouldn't start a whole army of rabbits in your backyard or anything. But the strange thing about these numbers is that's where they came from, but they show up in nature in unexpected places. You might think, like, you know, well, he just made this list up. There's a little, you know, technique to come up with them. Why would this show up in nature? Well, for example, as a simple example, go to your backyard and find a flower. And chances are, if you look at how many petals are on the flower, it will be one of these numbers. Not all the flowers, of course, but more often than not, it will be one of these numbers rather than just some random number of petals. This also happens with how the leaves grow around stems. And, well, I brought in a couple more to show you, like the pineapple I mentioned. I have this pineapple sitting here. So why would I bring in a pineapple for a math program? Well, I'll show you what's going on with this pineapple. Let me put this on my, I'm going to try and show this on my math cam. I don't know if this is going to work. Should work okay. So I'll zoom out here for you. All right, so here's my pineapple. What I wanted to show you was these little nodules are actually in a nice pattern here. In fact, if you look, they kind of form these diagonal spirals. So see this one right here? There's a spiral, and there's a bunch parallel to that. So if you watch that spiral, I could, you know, roll the pineapple around and see all these parallel spirals. And at the same time, there are some spirals that cut this way. So I also have, you know, kind of cutting diagonally the other direction, I have spirals. And you can even identify a third pattern of these little nodules, and that is sort of a vertical pattern. So they're kind of lined up this way as well. And again, you could map that out if you looked at all the sides of the pineapple. So it turns out, and this might seem like a strange coincidence, but if you count these spirals, I showed you 3 different ways to look at spirals. You get 3 different numbers of them wrapped around the pineapple. And I actually did this on this exact pineapple. The numbers I got were 8, 13, and 21. Well, hold on a second. Look at these Fibonacci numbers. So I'll zoom this back in for you. Look at the Fibonacci numbers, and you notice right in a row I have 8, 13, 21. Well, every pineapple I've seen does this. In fact, I'll show you, I have a version on my computer. This physical one's a little hard to show you in person. So I'm going to show you a pineapple I have on my computer. And this one someone has been nice enough to already mark these spirals for us. So there's some colored tape on here. You can see this blue tape right here is sort of those vertical spirals I showed you. And there's one here marked. I'm going to turn this a little bit. There's a spiral here marked with red and white tape, and it winds, almost all the way around the whole pineapple. And then there's another one from the same spot that winds to the left and up diagonally. And this one's a little shorter. And again, you can actually, turn this and sit there and count with your mouse, and you get the same numbers. You get 8, 13, and 21 of these spirals, which is a little strange. I mean, it seems a little bit, too weird to be correct, but it's actually true. Here's another picture. This is a pine cone, and you're looking at the base of the pine cone here. And actually, if you look at how these little, I don't know what you would call them, they're not really leaves, the little parts of the cone, they're arranged in spirals. And again, if you try and count these spirals walking around the circle, I did it on this picture, and I got 13 spirals one way and 8 another way, those exact same numbers. Here's a flower. I believe this is actually a daisy. This is the middle of a daisy here, and you can see all these little packed in, I don't know what you'd call them at the moment. They're going to be seeds eventually, but there's a whole bunch of them, and they're very tightly packed in there. And yet, someone has drawn a pattern of the spirals that they form. They're not just random. You can actually see spirals in the pattern here. And one set of spirals, there's 34 of them one way, and there's 21 of them the other way. Well, if you look at my list of Fibonacci numbers, again, those are exact Fibonacci numbers. Here's an even more complicated flower. This has tons of these little guys in the middle of it, and I mean, this is too fine for me to sit here and count, but I did it at home when I had more time, and there were 34 one way and 55 spirals the other way. Again, they're Fibonacci numbers. So if we have some time, I'll show you some more cool connections later with nature. It's really strange that this happens. I can give you a little bit of an idea why you would get these. I mean, it's not just coincidence. In fact, nature's being efficient here. It turns out that these numbers, the way they're added, has to do with efficient ways of, or efficient ratios of arranging things. And you know what? Plants are smart, or they've evolved to be smart. They arrange their leaves in ways that maximize the sun that they get. They don't want the leaves shading leaves below them. They maximize the number of seeds they can pack into the same, little circular space. And it turns out, when they do that, the optimum way to do it often relies on these Fibonacci numbers.